So we're going to talk about the mean value theorem today, and this is a little bit farther down the notes. We'll do this work on Wednesday. We'll talk about the beginning of the notes, but I actually want to go partway down the notes and talk about the mean value theorem. So here's my secant line. It goes from my start point to my end point. And the idea is that somewhere this slope will happen again on one of my tangent lines. In other words, the derivative at some point on the interval has to match up with this average rate of change, with the slope of the secant line. So I walked through the steps already of how that's going to work. So let's look at some examples, because I think that's going to help us here. All right. So we are finding the values of x where the slope of the tangent line equals the slope of the secant line. So find all values where f prime of c equals f of b minus f of a over b minus a. That's what we're looking for. So first off, we're going to find f of b minus f of a over b minus a. Well, here's a, and here's b. So we're starting at 0 and ending at 1. And the idea here is that we want, that means we want f of 1 minus f of 0 over 1 minus 0. So f of 1 minus f of 0 over 1 minus 0. Well, we need to find f of 1. That's going to be 1 plus 2 minus 1. So that's going to be 2. F of 0 is 0 minus 1. So that's negative 1. So we have f of 1 is 2 minus f of 0 is negative 1 over 1 minus 0, which is going to be 3 over 1, which is 3. We need f of b minus f of a over b minus a, and then the other requirements that we have are that f needs to be continuous and differentiable. So we're going to say since f of x is a polynomial, it is continuous. It's continuous and differentiable everywhere. So we're going to say that it's continuous on the closed interval from 0 to 1, and differentiable on the open interval from 0 to 1. That's our requirements for this to work. Continuous on the closed interval, differentiable on the open interval. Therefore, by the mean value theorem, there must be a value c on the interval from 0 to 1 where f prime of c equals 3. the f of b minus f of a over b minus a. We're guaranteed that this average rate of change, the derivative matches up with that average rate of change. In other words, we're guaranteed that the tangent line matches up with the secant line somewhere. So to figure out where that is, we can find f prime. Derivative here is going to be 2x plus derivative 2x is 2. So somewhere between 0 and 1, we're guaranteed that the derivative is 3. So we're going to set 3 equal to 2x plus 2 and figure out where it happens. Well, that's going to be at x equals, subtract 2, we get 1 divided by 2, 1/2. So just to give you an idea of like picture-wise what we're looking at 0, we're at -1, and at 1, we're up at 2. So what's happening here is that we have our slope of the secant line here, but then our graph is a parabola, so it looks something like this. And what we're saying is that at 1/2, our slope of the tangent line lines up with our slope of the secant line. Our derivative ends up being 3 at this point of 1/2. And this value is guaranteed to exist somewhere in the interval. That's what the mean value theorem says. So on the next problem, we're starting by writing down that f is continuous between -1 and 1 and differentiable between -1 and 1. Continuous on the closed interval, differentiable on the open interval. So that means the mean value theorem is going to apply here. I know that it's continuous and differentiable, by the way, because sine, the y values go between -1 and +1, and they exist everywhere in that interval. So that means that sine inverse, I can plug in anything between -1 and 1 and get out an angle measure. So let's work through this here. Sine inverse of 1. Where's sine 1? Well, sine is 1 at pi over 2. And where's sine -1? Well, sine is -1 at -pi over 2. And so when we do f of b minus f of a over b minus a, we want f of -1, or sorry, f of 1 minus f of -1 over 1 minus -1. So that's going to be pi over 2 minus a negative pi over 2 over 1 minus -1. Pi over 2 and pi over 2 is pi over 1 plus 1 is 2. So pi over 2 is the value that we're interested in. So that means by the mean value theorem, there must be a value somewhere between -1 and +1 where f prime of c is the f of b minus f of a over b minus a, is pi over 2. So we're saying somewhere in this interval, the derivative has to be pi over 2. And we can actually find where that happens. So let's see. Derivative of sine inverse of x is 1 over the square root of 1 minus x squared. And I want to know where that equals pi over 2. And so I'd solve this equation. So I do some algebra and get the answer. 2 stationary patrol cars are equipped with radar 8 miles apart on the highway as shown in the figure. As a sports car passes the first patrol car, its speed is clocked at 55 miles an hour. 6 minutes later, the sports car passes the second patrol car. Its speed is clocked at 50 miles an hour. So we have the 2 patrol cars, and they mark the person as going 55 at one point and 50 at another point. Speed limit's 55. We seem to be a-okay, except for the mean value theorem. The mean value theorem is going to catch them. So here's how that's going to look. First off, the function of the car f of t is the position of the car at time t. And f is continuous. So we're looking at t starting at 0 and ending at 6. Right? Those are the 6 minutes. So t is in minutes. So f is continuous on the closed interval from 0 to 6 and differentiable on the open interval from 0 to 6. So the reason we know that is because, well, since we're measuring position, then the derivative of position is velocity. So our velocity exists everywhere, and so does our position. You know, we're assuming that this car isn't somehow teleporting somewhere. And so it's driving along a highway as a normal car would. So that means the mean value theorem applies. So we can find f of b minus f of a over b minus a. Well, the interval we're looking at is between 0 and 6. F of 6 minus f of 0 over 6 minus 0. F of 0 is at 0. And f of 6 is at 8. So we have 8 over 6, which is 4/3. But remember that t was in minutes. So this is miles per minute. And so if we want to convert that to miles per hour, time to do some quick dimensional analysis here. Everyone's favorite. Well, 60 minutes to an hour. So that means we're going to multiply by this number by 60. So that leaves us to be 20. And 4 times 20 is 80 miles per hour. So by the mean value theorem, there must be a time in the interval 0 to 6 that the car was traveling 80 miles an hour. So even though the patrol car didn't catch anyone going over 50, we know that because of how fast they got from point A to point B, it was impossible for them to get there that fast without at some point traveling 80 miles an hour. Busted. So I'm going to talk about this one on Wednesday. I just want to look at where does the mean cases where the mean value theorem doesn't apply. So we're going to deal with each of these individually. All right. First off, f prime of x here is 1/3, bring the exponent out in front, x to the negative 2/3. So that means it's 1/3 times the cube root of x squared. And so hopefully you're seeing the problem here, which is that f prime of x does not exist somewhere in this interval because the bottom of the fraction can't be 0. So that means f is not differentiable. This derivative doesn't exist between -1 and +1. So the mean value theorem may not apply. I say may not because that doesn't mean it's impossible for it to be true. That let's actually test it. F of 1 minus f of negative 1 over 1 minus negative 1. Well, in this case, f of 1 is going to be 1. Cube root of 1 is 1. Cube root of negative 1 is negative 1. And so this is just going to be 2 over 2, which is 1. And so the mean value theorem would say that there's somewhere where this derivative is 1. In other words, where x to the 2/3 is 1/3. If I multiply by an x to the 2/3 here. So cube it, take the square root. So I would have the square root of 1 over 27. Actually, plus or minus. So in this case, it does work. There is somewhere where the derivative is 1 in this interval. So just because it may not apply doesn't mean it's impossible. It just means it's not guaranteed. So another way to say this is that it's not guaranteed to happen. Let's look at one more case. Absolute value. Well, absolute value is continuous, but if you remember absolute value, you'll know that it's a V shape. So it's going to be an upside down V. So at this point, we have a corner. So that's what we're going to find here. But let's put it in a more technical way here. Oops, I don't want that much. We're going to have a corner here. So we can actually write this as a piecewise function. Because as long as what's inside the absolute value is a positive, then we just have 1 minus x. But as soon as I have a negative number in here, I need to change the sign so that it's a positive. That's what absolute value does. So instead of 1 minus x, we're going to have 1 minus a negative x, the opposite sign of whatever we have. So that's going to end up being 1 plus x. So I can write it as a piecewise function here. So when I take my derivative, we run into a problem. We'll have to the left of 0 and to the right of 0. To the left of 0, the derivative of positive x is a positive 1. But to the right of 0, derivative of negative x is a negative 1. So that means that the limit as x approaches 0 from the left of f prime of x and the limit as x approaches 0 from the right of f prime of x, these don't match. From the left, we say we have a slope of positive 1. And from the right, we say that we have a slope of negative 1. This means since the limits from the left and the limits from the right, that means the derivative is not continuous at 0. This means f is not differentiable at 0. So the mean value theorem may not apply. It might not work. Just for fun, let's see if it does work. It worked last time, but it's not, again, the idea is that it's not guaranteed to work. So it might work, it might not work. F of 1 minus f of -1 over 1 minus -1. Well, that's going to be f of 1 minus the absolute value of 1 is going to be 0. And then absolute value -1 is still 1. So 1 minus 1 is still 0 over 2. So that's going to be 0. So what the mean value theorem would say is that the derivative is guaranteed to be 0 somewhere. Bad news. The derivative is either 1 or -1. Right? And if you think about the graph, it's 1 to the left is 0 and -1 to the right is 0. This is what the graph looks like. We're either having a slope of 1 straight line this way, or we're having a slope of -1 straight down this way. So that means, let me bring this back for a second. So that means I can never have a slope of 0. And it's because of this corner that it doesn't work. That makes the function not differentiable. So we can't guarantee the mean value theorem anymore. So that's why it's important to check if the function is continuous and differentiable in the interval. That's what guarantees that the mean value theorem works.